Hello, class. This is Dr. Mu-tor Flood. We are going to get into Chapter 7's lecture today, and it's going to be on probability and samples, the distribution of sample means. Hold on one second while I pull up that PowerPoint and share it with you. All right, so you should be able to see my screen now. And I'm going to go into slideshow. All right. So once again, this is chapter 7, probability and samples, the distribution of sample means. So the learning outcomes in this particular chapter is that we are going to define distribution of sampling means. We're going to describe the distribution by its shape, by what is called the expected value, and by a new thing that we're going to learn in this chapter, the standard error. Third, we are going to be able to describe the location of a sample mean by a z-score. And lastly, we are going to determine the probabilities that correspond to a sample mean using z-scores from the unit normal table. So some of the tools that you will need in order to be successful in this particular chapter are things that are carried from previous chapters. So you need to be comfortable with the random sampling that we talked about in chapter 6. And you need to be comfortable with probability and the normal distribution that we also talked about in chapter 6, as well as the z-scores that we started to discuss in chapter 5 and we talked about in chapter 6. So what you'll need to remember about that random sample, right? Remember that a random sample is a sample produced by a process that assures that, again, each individual in the population has an equal chance of being selected, and that the probability of being selected stays constant from one selection to the next when more than one individual is selected. And this requires what we discussed last lecture, which is called sampling with replacement. All right, so samples, populations, and the distribution of sample means. Right, so the location of a score, right, a raw score in a sample or in a population can be represented with a z-score. And researchers typically want to study entire samples rather than single scores. All right, samples are going to help provide us with an estimate of the population. All right, what we've been calling inferential statistics, right? So tests involve transforming a sample mean into a z-score. All right, so sampling error, right? We talked about that all the way in chapter 1, right? So this error, right, the sampling error, it doesn't mean that a mistake was made by the researcher. The sampling error is going to be what we talked about in the first chapter, is the natural discrepancy or the amount of error between a sample statistic, right? In this case, a sample mean, which is going to be the statistic that's the underlying a lot of these statistics that we're going to use going forward. So it's the amount of error between a sample mean, that's the sample statistic, and its corresponding population parameter, i.e. the population mean, all right? These samples are going to be variable, meaning they change, they fluctuate, all right? Two samples are very, 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 very unlikely to be identical. That is very rarely happens. And that's an important takeaway point. All right, so the distribution of sample means. So like we said in the last slide, samples are going to differ from each other, right? you take a sample from a population, that particular sample is not going to be equivalent to a second sample that you may take from the same population. All right. So samples differ from each other. And given a random sample, it is unlikely that the sample means would always be the same. All right. So that sample statistic is not going to be the same for all the samples you take from a population. They're going to be different. Now, the distribution of sample means is going to be the collection for all possible random samples of a particular size that can be obtained from a population. All right, I'm going to repeat that again, right? So in a distribution, right, a distribution of sample means. So just like we've been talking about a population distribution, a distribution of scores, now we're talking about a distribution of samples. So all the points in here, right, they previously were just individual scores. Now all those points making up the distribution are actual samples. And then specifically, they are sample means. All right. And so this is saying is that the distribution of sample means is the collection of sample means for all possible random samples. So we're doing the independent random sampling of a particular size, right? The sample size that can be obtained from a population. So if I have a population, a sample size of 10, right? So what this is saying is that all of the sample sizes, all of the samples of a sample size 10 that I can take from this particular distribution of sampling means, all right, it represents this distribution of sample means. So all of the sample sizes of 10 that have a sample, we're going to calculate the sample mean for it. And all those sample means piled up is going to become what is called the distribution of sample means. So it's a whole bunch of sample means of a certain sample size. For all the possible sample sizes, for all the means of a particular sample size. And we're going to put them all together in a distribution, and that distribution is called the distribution of sample means. Let's talk more about that. So sampling distribution. So distributions, again, like I said earlier, in the earlier chapters were distribution of scores from samples, right? A sampling distribution is a distribution of statistics, right? They're not scores, they're statistics. The distribution of sample means is a special kind of population, all right? So the distribution of sample means is going to be obtained by selecting all the possible samples of a specific size from a population. So let's look at this in a different way, right? So in this figure, this is the process of constructing the distribution of sample means. A sample of n scores is selected. Then the sample mean is computed, right, and placed in a frequency distribution, right, that we talked about in chapter 2. This process is repeated over and over again until all the possible random samples are obtained and the complete set of sample means is in the distribution. So here's our population of scores, right? We're going to take a random sample out of this population of a certain sample size, and then we're going to compute a sample mean for it. And then we're going to take that sample mean and put it into a frequency distribution table. All right, this right here. All right. And so this frequency distribution table, when we have taken all of the sample means of a certain sample size and put it into this frequency distribution table, This will be called a distribution of sample means, right? A distribution made up of sample means. So some important characteristics of distributions of sample means. So the sample means are going to pile up around the population mean. All right. The distribution of the sample means is going to be approximately normal in shape, which helps us to be able, if it's normal in shape, then we are able to use our unit normal table, right? Made up of the z-scores and the proportions that we talked about last week. Most of the samples should have means that are going to be close to the population mean. And it should be relatively rare to find sample means that are very different from the population mean. So the sample means, again, pile up in the center of the distribution around the population mean. And the frequencies should taper off as the distance between the sample mean and the population mean increases. Right? Now, the larger the sample size, right, the closer the sample means should be to the population mean, because a larger sample should be more representative. All right, so think about it. If I let's see, a good example of this. If I was trying to find out, let's say my variable is height, right? And I found out the height of every person of the entire population of students here at Bethune-Cookman, all 3,000 of y'all, right? And then I took a sample, right? I took a sample of 5 students attending Bethune-Cookman University and measured their height. Well, the sample average height and the population average height, they're more likely to be very, very different from each other. And that's because the sample size is very small, right? But let's say I took, let's say I increased the sample size from 5 all the way to 2,500 students out of the 3,000 students who attend Bethune-Cookman University. Well, now my sample size is incredibly large. So it is more likely that because I have this very, very large sample size, that it is going to more accurately reflect the population parameters of the population that it came from, just because the sample size is that much larger. I'm using more and more of the population that the sample comes from. So the larger the sample, the more closely it's going to approximate the population. All right. So sample means with a large size should cluster relatively close to the population mean, and the means obtained from small samples should be more widely scattered. All right. And we'll talk more about that. So here we have a population frequency distribution histogram, right? So in this population, we have a population of scores, right? And it scores, so N, this is the population. So the total number of scores is 2, 4, 6, and 8. And if we add all that up, right, 2 plus 4 is 6, plus 12, plus 8 is 20, right? 20 divided by 5 gives us, 20 divided by 4 gives us 5. So the population mean, right, is 5. All right. So we're going to continue to work with this, right? So add it all up, the population mean is 5. And we're dealing with a population of scores. All right. So now let's say, right, for that same population of scores, 2, 4, 6, 8, with a mean of 5, right? Let's say we take samples of a sample size of 2, right? And we take all the possible samples of a sample size 2 from this population of scores, all right? And notice that we are going to use random samples, and that this requires sampling with replacement, all right? So it is possible to select the same score twice, right? So if we took a sample with a sample size of 2, right? N equals 2, right? So in our first sample, right? Let's say we grabbed the population of scores, um, from a bag or from a hat, right? So the first score is 2, the second score is 2, right? Then because we're doing sampling with replacement, we put all those 2 back, right? And then our second sample of a sample size of 2 is 2 and 4, right? And then the next one is 2 and 6, and then 2 and 8, all right? And then we do that for all of the possible sample sizes that we could get for a sample size of 2. And that ends up being, we can get 16 different samples, 16 different samples. And so if we were to average those out and get the sample mean for each of those samples. So the sample mean for a sample size of 2, where the first score is 2 and the second score is 2, well, the sample mean would be 2. For the next one, 2 and 4 is 6. 6 divided by 2 is 3. So here are the sample means for each of those samples, right? The total number of samples is 16. Those are all the possible samples that we can get for a sample size of 2 with a population of scores that are 2, 4, 6, and 8. All right, so if I average out all those samples, right? And then to get sample means, and then I added up all of those samples, I added up all the samples, the sample means, I should say. I added up all the sample means, all right? And then I divided by the number of samples, right? So it would be 80 divided by 16, which is the number of samples that we have. We have 16 samples. All of this added up is 80. So 80 divided by 16 is 5. All right. So where did we see that 5 at before? Right. Let's go back to the previous slide. Right. So the sample mean average. So the average of all of the possible sample means of a certain sample size. In this case, the sample size was 2. Right. And then in this one, it added up to 5. Well, we've seen 5 before, right? 5 was the population mean, right? 5 was the population mean. So what I'm trying to tell you is that the sample mean average is going to be equivalent to the population mean, all right? The average of all the sample means of a certain sample size is going to be equivalent to the population mean, all right? And this doesn't matter what size the sample is, the sample sizes could be 5. If we take all the possible samples with the sample size of 5 and we calculate a mean for all of them, and then we average all of those sample means from all of those samples, that sample mean average is going to be equivalent to the population mean that those samples came from. All right. So we're going to talk more about this. So here is the distribution of those sample means that we were just working with, right? We had 16 of them, right? And our population of scores, again, were 2, 4, 6, and 8, right? So these are the sample means. So the sample mean of 2, there was 1 sample mean of 2, there were 2 sample means of 3, there were 3 sample means of 4, there were 4 sample means of 5, there were 3 sample means of 6 and 2 sample means of 7 and one sample mean of 8. All right, and as you can see, if we plotted all of those samples that we had out, right, they form a normal distribution, right, where the majority of the sample means are relatively close to the average of the sample means, which again is equivalent to the population mean. All right. So most of the scores are close to the population mean. I mean, most of these sample means are close to the population mean. And as we get, I guess, in any normal distribution, as we get further out, right, the frequency of those particular sample means gets smaller and smaller. So the frequency of having a sample mean of 2 and a sample mean of 8 is smaller than having a sample mean of 6 or 4 or 5. All right. Okay, so let's continue with this. So using that same distribution, right? So you should realize that we can use the distribution of sample means to achieve the goal for this chapter, right? Which is to answer probability questions about sample means. For example, if you take a sample of 2 scores from the original population, what is the probability of obtaining a sample with a mean, a sample mean that is greater than 7? So written, we have probability, and in parentheses, we have the event. And the event is a sample mean that is greater than 7, right? Because probability is equal to proportion, the probability question can be restated as follows. So of all the possible sample means, what proportion have values greater than 7? In this form, the question is easily answered by looking at the distribution of sample means. All the possible sample means are pictured, and only one out of the 16 means has a value greater than 7. Therefore, the answer is 1 out of 16, or P equals 1/16. So let's look at that again, right? So it asks, what is the probability of getting a sample mean that is greater than 7, right? Well, there are the total number of possible outcomes are 16. There are 16 sample means. So that is the denominator. How many of those sample means are greater than 7? Well, there's only one, and there's a sample mean of 8. So the answer would be 1/16. Probability of getting a sample mean that is greater than 7 is 1/16. Okay. So with that in mind, let's do some questions. All right. See if we can't figure a lot of these out. So if all the possible random samples, right, each with a sample size of 9, are selected from a normally distributed population, that's important, right? It's normally distributed with a population mean of 90 and a standard deviation of 20. And the mean is calculated for each sample. Then what is the average value for all the sample means? Well, the average value for all the sample means of a certain sample size, in this case, a sample size of 9, is going to be equivalent to the population mean that it came from. So the population mean is 90. So the answer is going to be 90. All right. So question 2, all the possible random samples, right, of a sample of a size of 2 are selected from a population with a population mean of 40, and a standard deviation of 10. And the mean is computed for each sample. Then all the possible samples of size 25 are selected from the same population, and the mean is computed for each sample. How will the distribution of sample means for the sample size of 2 compared to the distribution of a sample size of 25? Well, let's think about this. I didn't directly tell you how to do this, but we should be able to figure it out. We talked about, hey, the larger the sample size, right? The closer, right? The sample means are going to be to the population mean. So if we were drawing a distribution, right? If we had a sample size of 2, right? The sample means are going to be more spread out. They're going to be more scattered when the sample size of the sample means is 2. However, if we have a larger sample size, and then we calculate the sample means, and to get our distribution of sample means, our distribution is going to be skinnier. Oh, yikes. Give me a second. Okay. So our distribution, is going to be skinnier. Oh, yikes. What's happening there? Okay. And that's because we have a larger sample size. And so when we calculate our sample means are going to be closer to the population mean. So we're going to have a skinnier distribution where the sample means are clustered tightly around the population mean. So what is that in words? What does that kind of look like? So that looks like what is D, right? The variability, right? How the sample means vary for the sample size of 25 is going to be smaller than the variability for the sample size of 2. But the two distributions are going to have the same mean, right? So again, if we average out all the samples of a particular sample size, doesn't matter how large or small the sample size is, if we take all of these sample sizes for and calculate the sample mean, the average of those sample means are going to be equivalent to the population mean. All right, going to be equivalent to the population mean. So number 3, if all the possible random samples of a sample size of 25 are selected from a population with a sample mean of 90 and a standard deviation of 20, and the mean is computed for each sample, then what shape is expected for the distribution of sample means, right? Well, the sample means are going to form a normal shape distribution like they did in the example that we worked on here, right? These are all the sample means, right, of a certain sample size. And when we plotted them all out, they created a normal distribution. All right. So it creates it forms a normal shaped distribution. All right. So let's continue. Here are the answers. All right. So the shape, the central tendency, and the variability for the distribution of sample means. So we have the first one, the first concept is what's called the central limit theorem. And this is used to specify the shape, central tendency, and variability of the distribution of sample means. The next is what is called the standard error of the mean, or the standard error of M, right? And this measures how well an individual sample mean represents the entire distribution. So let's first deal with that central limit theorem. So the central limit theorem is going to apply to any population with a mean and a standard deviation. The distribution of sample means approaches a normal distribution as the sample size gets larger, right? And the distribution of sample means for samples of a certain size will have a mean. We'll have a mean of the distribution of sample means. All right. So we kind of already talked about that, right? So if you add up all of the sample means of a certain sample size, you're going to get what's called the mean of the distribution of sample means. And that mean of the distribution of sample means is going to be equivalent to the population mean that those samples came from. And so the distribution of sample means for samples of a certain size will have a standard deviation that is calculated like this, which is going to be the standard deviation, the population standard deviation, divided by the square root of the sample size. So some more observations about this. So this standard deviation for sample means, again, is called the standard error of the mean, or usually just standard error, right? So as the sample size gets larger, right? Usually when we mean large, we mean the sample size is 30 or above. As the sample size gets larger, the sample mean will approach a normal distribution. The mean of a distribution of sample means, again, like I said, is going to be equivalent to the population mean. A third important point is that the standard deviation as a measure of variability for the distribution of sample means is calculated like this, right? So in this way, you can get the variability, right? The standard deviation divided by the square root of the sample size. You can also get the shape, right? If it's a sample size of 30 or more, it is normal. And you can get the central tendency, which is the mean, right? You can get all that information, right, from using the central limit theorem and reading the information that is provided to you about particular distributions of sample means. All right, so in talking about the shape of the sample means, so the distribution of sample means is almost perfectly normal in either of two conditions, right? So if the population that the samples are selected from is a normal distribution, then the distribution of sample means is going to be normal as well. Or let's say we don't know this, right? If our sample size is 30 or more, then we're going to say that this is going to conform to a perfectly normal distribution. Has to have one or the other or both. Okay. So next we will deal with the term what's called the expected value of M. All right. So the mean of the distribution of sample means is this right here, the mean of the distribution of sample means. And it has a value equal to the mean of the population of scores. So the mean of the distribution of sample means is equal to the population mean. All right. And so the mean of the distribution of sample means is also called the expected value of M, expected value of the mean. And the expected value of the mean is what we would consider to be an unbiased statistic, because the mean of the distribution of sample means, all right, also known as the expected value of the mean, all right, is the value of the population mean, right? If you average all of those sample means of a certain sample size, you are going to get what the population mean of the scores are, right? If we got any number other than that, then that particular statistic would be a biased statistic because you would either be underestimating or overestimating what the population parameters are. In this case, the population mean, but it doesn't. It gives you the exact population mean, right? And so it becomes an unbiased statistic. All right, let's continue. All right, so let's talk more about that standard error of the mean, or just the standard error. So the standard error, right, is going to be the variability of a distribution of scores, and it's measured by the standard. I'm sorry. Let's go back. When we dealt with regular variability of a distribution of scores, what we used to measure it was the standard deviation. However, when we're measuring the variability of a distribution of sample means, right? We went from scores to sample means. Well, that's going to be measured by the standard deviation of the sample means. And that is called the standard error of M, or just the standard error. And you will also see it look like this, right? It is the population standard deviation with a subscript of M, right? So in journal articles or other textbooks, the standard error of M might be identified as either the standard error or SE or SEM. And so the standard error of the mean is computed like this, where we already seen how this is computed. It's going to be the standard deviation divided by the square root of the sample size. And we're going to talk a little bit more about that. So the definition of the standard error of the mean. So again, the standard error of the mean is the standard deviation of the distribution of sample means. When the standard error of the mean is large, that means the sample means, are widely scattered. All right. So you'll get a fat distribution, right? Because all the sample means are far away from the population mean. When the standard error of the mean is small, the means are clustered closely, like the example we did, right? Let's give a better one. So it'll be something like this, right? Which is, we're saying that the sample means are clustered very tightly around the population mean. And so the standard error of the mean is going to provide a measure of how much distance is expected on average between the sample mean and the population mean. So when we did the standard deviation was a measure of how much distance is expected between the score and the population mean or the sample mean, right? But a standard error of the mean is providing a measure of how much distance is expected on average between a sample mean and the population mean. All right, so we're moving from scores to samples in this particular chapter. So standard error magnitude, right? We have something called the law of large numbers, which I've kind of touched on already, but the larger the sample size, the more probable it is that the sample mean will be close to the population mean. And I kind of discussed that when I gave you the example of the Bethune-Cookman students, and when we had a sample size of 5, and then we had another sample size of 2,500, right? The larger the sample, the closer it is. The closer it is, closer the sample mean is going to be to the population mean. Population variance. The smaller the variance in the population, right? The smaller, so with the smaller the scores are scattered, right? So this variance has to deal with variability. And they're saying, hey, if the scores in the population don't vary a lot, right? If they don't vary a lot, then the more probable it is that the sample mean is going to be close to the population mean, right? So the closer the numbers are in the population, well, if we pull from that population, we get a sample of a certain size, and then we calculate the sample mean. Well, the sample mean is going to be closer to the population mean because the population of scores have less variability. All right. And so this figure is showing the standard error and the sample size relationship. All right. So on the x-axis, we have the number of scores in a sample. It's going up from 1 all the way to 100, right? So as the scores in a sample increase, right, the standard error is going to decrease, right? There is an indirect relationship between the two. As the number of scores in a sample go up, standard error goes down. As standard error goes up, the number of scores go down. All right. So this is the standard distance between a sample mean and a population mean, right? So again, as the sample size increases, there's going to be less error between the sample mean and the population mean. Less error. So they're going to be closer and closer together. The larger the sample size gets, the closer and closer and the less error there's going to be between sample means and the population mean that the samples come from. So let's do some calculations to kind of formally look at how that relationship looks, right? So let's say we have a sample size. All right. So these calculations for the points and figure 7.3, I don't think I had that in our slides. But again, notice that the size of the standard error decreases as the size of the sample increases, right? Again, it's their indirect relationship. As one increases, the other one decreases. So if a sample size is 1, and we calculate the standard error, it's going to be, let's say the standard deviation was 10. All right, I don't have that slide in here. The standard deviation is 10. Well, to calculate the standard error of the mean, it's going to be, again, the standard error of the mean is going to be the standard deviation divided by the square root of the sample size. So the standard deviation is 10 over the square root of 1. Well, that's going to give us 10, right? That's the standard error is 10. But now let's say we increase the sample size to 4. Well, 10 over the square root of 4 is 5, right? So just going up in sample size by 3, half this out. The standard error went from 10 all the way to 5. If we have a sample size of 9, well, we plug that in here. 10 over the square root of 9 gives us 3.33. So as you can see, the standard error is getting lower as the sample size increases. So let's take 16, right? Now the sample size is 16. And we put it in here. 10 over the square root of 16 will give us 250. All right, and 25. The sample size is 25. Well, we put that in here. 10 over the square root of 25 gives us a standard error of 2. And so on and so forth. But as you can see, it doesn't get much lower the further the larger the sample size gets, right? The difference between a standard error of 2 and 1.43 is small. It's not like how it was when we went from a sample size of 1 to a sample size of 4, right? That halved it out. Each other one, as we making the sample size larger, the standard error gets smaller, but by less and less amounts, right? All right. Let's see. Let's continue. All right. So we also have an alternate standard error formula, and this alternate standard error formula is one that is versions of this that we're going to use in future chapters. So the population standard deviation and the population variance are directly related. And it is easy to substitute variance into the equation for standard error. So using the simple equality where the standard deviation equals the square root of the population variance, the equation for the standard error can be rewritten as follows. So the standard error equals, this right here, which also equals the standard deviation over the square root of the sample size, or what is functionally equivalent to this is the square root of the sample variance over the square root of the sample size, or just the square root of the sample variance, of the population variance over the sample size. And so throughout the rest of this chapter, right, we're going to continue to define standard error in terms of the standard deviation. However, again, like I said, in later chapters, right, we're going to use a different formula to calculate the standard error. All right. And so if samples, let's do some of these questions. If samples are selected from from a population with a population mean of 50 and a standard deviation of 12, then what is the standard error of the sample means for a sample size of 4 and a sample size of 16? Well, let's do the math on this, right? So they're basically asking us just to calculate the standard error. So we know the standard error, right, that we're using right now is going to be the standard deviation divided by the square root of the sample size. All right, so the first one has a sample size of 4, right? And a standard population standard deviation of 12, right? So we just plug it in. So 12 goes into the numerator. That is the population standard deviation. The sample size is 4, and we're going to take the square root of that 4, right? So that gives us 12 over 2, which gives us 6, which is this one right here. All right. So let's try the other one. The other one said, hey, the sample size of 16. Well, we should already know, right? If we're using the same population mean and the same standard deviation, if we increase the sample size, then our standard error of the mean should get smaller, all right? Because of what we did right here, right? It should get smaller. As sample size increases, standard error gets smaller, right? We know that. So let's see. In this one, the standard deviation for the population is still 12, and the sample size is 16, right? So we're going to take the square root of that sample size, and that's going to give us 12 over 4, which equals 3, right? And so 3 is smaller than 6. So yes, as sample size increases, the standard error is going to get smaller. All right, so the distribution of scores versus sample means. So in the original population of IQ scores, so we're dealing with population IQ scores, right? The population mean is 100 and the standard deviation, population standard deviation equals 15. So let's say we took a sample of 25 IQ scores, right? Because of sampling error, right? The mean is 100, the sample mean is 101.2, which is different from the population mean. And the standard deviation, that looks, well, this should really say S. All right, so don't look at that. So the sample mean, the sample standard deviation equals 11.5, right? So that's what's called sampling error. Samples are going to be different from the populations that they came from, all right? And so the distribution of sample means, right? The sample means for all the possible random samples of 25 IQ scores, right? Well, that's going to give us a population mean of 100, right? Because the average of the sample means is equivalent to the population mean, right? So remember this, UM, all right? The distribution of sample means is going to be equivalent to the population mean, all right? Those are equivalent. And the standard error of the mean is going to be 3, right? We know it's 3 because we have a sample size of 25 and a standard deviation of 15, right? So 15 divided by the square root of 25 gives us 15 over 5, which equals 3. So the standard error of the mean equals 3. So what I want to stress that each of these three different kinds of graphical representations of distributions, they have their own shape, mean, and standard deviation, right? So this one had the standard deviation for, A had the standard deviation for the population, right? The population. And this one had a sample, mean and a sample standard deviation that was different from A. And C is the distribution of the sample means with a sample size of 25. And this one had a standard error of 3, right? So those standard deviations, right, from the original population of scores to a sample, one sample, to a distribution of sample means are all going to have different standard deviations and standard errors. All right. So this is just another way to look at it, right? So in this one, the original population IQ scores, let's say was the population mean is 100 and the standard deviation is 12. Let's say we took a random sample of 16 scores from this population. We calculated it and we got a sample mean of 98.75 and a sample standard deviation of 9.88, right? If we then took a distribution of sample means for all of the possible random samples with a sample size of 16, well, the population mean is going to equal the distribution of the average of all the sample means in the distribution, right? So that's going to be the same, but we're going to have a standard error of 3. All right, and so how do we get that standard error of 3? Well, the standard deviation, right? It's going to be a standard deviation over the square root of the sample size. So the standard deviation is 12. and the sample size is 16. So 12 over 4 gives us 3. So the standard error of the mean is 3. All right. So let's do a learning check, right? So a population has a mean of 65 and a standard deviation of 16. So we're going to describe the distribution of sample means by their shape, central tendency, and variability for a sample size of 4 selected from this population. Well, we can get the standard error for this, right? So the standard error is going to be, again, the population standard deviation over the square root of the sample size, right? So that's going to be 16 over the square root of 4, which equals 16 over 2, which equals 8. So the standard error of the mean is 8, all right? Now, the shape of the distribution is going to be unknown, right? And why is that? Because the sample is not large enough to guarantee a normal distribution, and we don't know the population shape, right? So in a couple of slides ago, I said, hey, in order for us to be able to know the shape of these things, we need to know if it's a normal distribution or if the sample size is 30 and over, all right? But this one had a sample size of 4, and it didn't tell us that the sample mean comes from a population with a normal distribution. So we can't answer what the shape is, all right? Can't answer what the shape is. However, what we can do is we can tell you what the central tendency is, right? The central tendency would be 60, a mean of 65, right? Because the distribution of sample means is going to be equivalent to the population mean. All right, so let's do B. Describe the distribution of sample means, the shape, central tendency, and variability for samples of size n equals 64 selected from this population, right? Well, now the sample size is large enough, right, where we can talk about the shape, right? And not just the central tendency and the variability. So let's do that, right? So to get the standard error of the mean, it's going to be, again, the population standard deviation divided by the square root of the sample size. And so that is going to be 16 over the square root of 64, which equals 16 over 8, which gives us 2. So the variability is the standard error of the mean. Variability is going to be 2. The shape is going to be normally distributed because the sample size is over 30. So we're going to assume that it's that's from a normal distribution. And the central tendency is still going to be 65 because if we take the average of the sample means, right, and we average those sample means out, it's going to, that distribution of sample means, or the average of the sample means, is going to be equivalent to the population mean. All right, so number 2, describe the relationship between the sample size and the standard error of the mean. Well, we talked about this already. The standard error decreases as the sample size increases. All right, and so the third question is, for a population with a population mean of 40 and a standard deviation of 8, The standard error for a sample mean can never be larger than 8, right? Well, that is going to be true, right? And that's because if we had a sample size of 1, right, the standard error is going to be 8, right? So if we don't remember this, we can just try it out. So the standard error of the mean is, the formula for it is the standard deviation over the square root of the sample size. So the standard deviation is 8, and the square root of 1, right, is 1. So 8 over 1 equals 8, right? So the standard error for a sample mean can never be larger than the standard deviation. Okay. And here is the answers to the question. We're going to skip these because we kind of answered those already. Okay. All right. So z-scores and the probability for sample means. All right. So the primary use of the distribution of sample means is to find the probability associated with any particular sample and their accompanying sample means. Proportions of the normal curve are going to be used to represent probabilities. We're going to calculate a z-score for a sample mean, right? Before, we were calculating z-scores for an individual raw score. But now we're going to calculate z-scores for sample means. All right, so what are the equations for that? Well, a z-score for sample means. The sign is going to tell us whether the location is above or below the mean, right? So positive is above the population mean, negative is below the population mean. And again, the number is going to tell us the distance between the location and the mean in standard deviation, but more specifically standard error units, because we're using the standard error of the mean. And so the formula looks like this. It's going to be z equals the sample mean minus the population mean divided by the standard error of the mean. And now let's say we wanted, let's say they gave us the z-score, right, for a particular sample mean, and they wanted us to compute what that sample mean was. Well, we would use this formula, all right? So these are similar to what we have discussed last week, except now we're using standard error in place of standard deviation, and we're working with sample means instead of raw scores. So to get the sample mean, the original sample mean, it would be the population mean plus the z-score times the standard error of the mean. All right. So let's try an example of this, right? So a sample of for a sample size of 4 scores is selected from a normal distribution, right? So it's a normal distribution, right? With a mean of 40 and a standard deviation of 16. Find the z-score for a sample mean of 42. All right, so that's the first part. Let's just deal with that first, right? So z, to find the z-score, it's going to be the sample mean minus the population mean over the standard error of the mean. And so we have the sample mean is 42 minus the population mean of 40 divided by the standard error of the mean. Well, we don't have that yet, right? So we're going to have to calculate that, right? So let's calculate that standard error of the mean. So the standard error of the mean is going to equal the standard deviation over the square root of the sample size. So the standard deviation is 16. The sample size is 4. All right. So 16 over 2 would give us a standard error of the mean of 8. So, so we put that right there. 42 over 40. 42 minus 40 over 8 is 2 divided by 8. And that is going to give us a z-score of 0.25. All right. And so the next question is, determine the probability of obtaining a sample mean larger than 42. So let's write that out. So the probability of obtaining a sample mean that is larger, that is larger than 42. All right. So in this one, we've already converted this into a z-score, right? Right. And so the z-score is 0.25, right? So if we drew a distribution, right, put the sample mean, nobody put the population mean. Population mean is 40, right? And we are going to discuss where our sample mean is. Our sample mean is at 42. So our sample mean is above the population mean, right? So we already know that a z-score is going to be positive, like it was here. The z-score was already positive, right? It's asking us to look for what is the probability of obtaining a sample mean that is greater than 42. So we're looking for everything above a sample mean of 42. So the z-score bisects, right? Bisects the distribution and breaks it up into two parts, just like we talked about last week. So the two parts are going to be a body and a tail, right? The tail is going to be the smaller part. The body is going to be the larger part, right? It doesn't matter if we're dealing with, sample means or individual scores. The same logic applies. So for this one, we are looking for a tail. We're looking for a tail, right? That's the smaller portion. So let's go to our unit normal table and look that up. Okay, let's make sure you could see this. Yikes. Hmm. Give me a second. One second, y'all. Trying to figure out something. Why is that not doing that? I guess. Hmm. give me, sorry about that. Give me one more second. So why won't it let me out of this? Okay, let's get out of that one. And share the screen. Okay. All right, so you should see the unit normal table now. All right, sorry about that. Had some technical issues. All right. And so if we have a z-score of 0.25, right, we're going to go into unit normal table and look where the z-score of 0.25 is. And we are looking for the proportion in a tail, right? And so the proportion in a tail is 0.4013. All right, 0.4013. Okay. Okay. All right, so you should be able to see this. Okay, so another example. So suppose the population of scores on the math SAT forms a normal distribution with a population mean of 500 and a standard deviation of 100. If you take a random sample of 16 students, what is the probability that the sample mean will be greater than 525? Well, first, you're going to restate this probability question as a proportion question. So out of all the possible sample means, what proportion have values greater than 525? You know about all the possible sample means. This is a distribution of sample means. The problem is to find a specific portion of this distribution. Although we cannot construct the distribution of sample means by repeatedly taking samples and calculating the means, we know exactly what the distribution looks like based on the information from the central limit theorem. Specifically, the distribution of sample means is going to have the following characteristics. The distribution is normal because the population of SAT scores is normal, right? The distribution also has a mean of 500 because the population mean is 500. And if the sample size is 16, the distribution has a standard error of 25. And so the distribution of sample means is shown in figure 7.6. And so what we're interested in is the sample means greater than 525. So the next step is to use a z-score to locate the exact position of a sample mean of 525 in the distribution. All right. The value 525 is located above the mean by 25 points, which is exactly one standard deviation. In this case, exactly one standard error. Thus, the z-score for a sample mean of 525 is z equals 1. Because the distribution of sample means is normal, you can use a unit normal table to find the probability associated with the z-score of 1. The table indicates that 0.1587 of the distribution is located in the tail of the distribution beyond the z-score of positive 1. So our conclusion is that it is relatively unlikely, right? It only has a 15.87% chance to obtain a random sample with a sample size of 16 that have average math SAT scores greater than 525. So here is that question shown graphically. So here's the distribution. Here's the standard error, right? And here is the shaded part that we were looking for, which means it's a tail, right? Here is the z-score, right? So we changed the 525 into a z-score, all right? And then we looked up this z-score in our unit normal table and looked under column C, which has the tail, all right? In order to get our answer of the proportion or percentage that make up scores that are greater than 525. So the middle of the distribution of sample mean questions, right? Just like we talked about the middle questions with the term middle in it last week, we can talk about that with the distribution of sample means. So this, let me show you what the setup for this question looks like. So this is the next slide, right? All right, so let's explain it. So the middle 80% of the distribution of sample means for a sample size of 25 samples. Samples were selected from a normal population with a population mean of 500 and a standard deviation of 100. All right. So in this question, right, they're asking what is the middle 80% of the distribution of sample means, right? Given that it's a sample size of 25, right, for all the sample means, and you have a population mean of 500 and a standard deviation of 100. So for this kind of question, right, you are going to look for the z-score boundaries and raw score boundaries, right? So first, you are going to calculate the standard error of the mean. Then you're going to break this up into two parts, right? That 80% middle, right? We're going to divide it by 2 to get 40% or 0.4000 and look up the proportion in column D, right? That tells you the proportion between the mean and a z-score. And then you're going to look up the corresponding z-score to that proportion in column A. Then you're going to plug the z-score into the sample mean equation, right? This is the sample mean equation. The mean equals the population mean plus the z-score times the standard error of the mean. And what you get for that, for this particular question, is 500 plus 1.28 times 20, right? Well, that shouldn't be 20, that should be 100. Let's see. Okay, so this should say, sorry, this should say 20. The standard deviation is 20. Oh, no. Oh, no, I'm sorry. No, this is, yeah, no. This is a standard error. So don't mind me with that one. Yes. The standard deviation is 100, but the standard error is 20. So let's confirm that. So 100 over the square root of the sample size, which is 25. So 100 over 25. Oh no, 100 over 5 gives us 20. All right, so yes. So we have 500 plus 1.28 times 20 and 500 minus 1.28 times 20. All right. And so for this question, it's going to give us the 80% of the scores that are in between, in the middle 80%. What are the boundaries of those? Well, it's 474.4 and 525.6. All right. And those correspond to z-scores of negative 1.28 and positive 1.28. So it is just like the questions that we did last week, except instead of using raw scores, we're now using sample means. So same exact kind of question. All right, let's see. All right, so thus 80% of all the possible sample means are going to be contained between 474.4 and 525.6. If we select a sample mean of 25 students, right, we can be 80% confident that the mean math SAT score for the sample will be in this range. The point of this question is that the distribution of sample means makes it possible to predict the value that ought to be obtained for a particular sample mean. Because the population mean is 500, and we know that a sample size of 25 students ought to have a mean math SAT score around 500. More specifically, we are 80% confident that the value of the sample mean will be between these two numbers. All right. The ability to predict sample means in this way will be a valuable tool for the inferential statistics that follow. In the future, we're going to calculate something called confidence intervals. All right. And this is going to help us do that. All right. Let's see. All right. So let's do some questions, right? So a sample of 25 scores is obtained from a population with a population mean of 70 and a standard deviation of 20. If the sample mean is 78, then what is the z-score corresponding to the sample mean? So for this one, all we're going to do first, is we're going to calculate the standard error, right? And then we are going to calculate the z-score. So the standard error is going to be, right? It's going to be the standard, the population standard deviation divided by the square root of the sample size, which is 25. Oh, wow, I guess I shouldn't write that in there. So the standard deviation is 20. So 20 over 5 gives us 4, right? So 4 is our standard error. Then we're going to plug it into our z-score formula for sample means, right? So the z-score formula for sample means is going to be the mean minus the population mean over the standard error of the mean. And so that is going to be the mean is 78 minus the population mean, which is 70, divided by the standard error of the mean, which is 4. So that's 8 over 4, which equals 2. So our z-score is positive 2, right? Z-score is positive 2. All right, so let's erase this. And we're going to be using these formulas again, so I'll keep the formula. Okay, so let's say a random sample of 4 scores is obtained from a normal population, right? With a population mean of 20 and a standard population standard deviation of 4. What is the probability of obtaining a mean greater than 22 for this sample, right? So for this one, they're going to start us off with, the sample mean, right? And they want us to find out a probability, right? So we're going to go from a sample mean, right, to getting a z-score, and then from the z-score to getting the probability. All right. So just let me pull something up to make this clear. Let's see. Stop the share. I'm going to pull up what we did in last week's lecture. Oh, yikes. Okay. 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 All right, so let me share my screen again. Okay, so you should be able to see my screen now. This is the, from chapter 6, right? This is the kind of a cheat sheet on what to do, right? But the only thing that we're going to change in this, right, is that we're not starting with X scores anymore. Now we're starting with sample means. So that's really the only thing that's changed from this, right? So if they give you the sample mean and they ask you to find a proportion, well, you're going to take the sample mean. You are going to then find a z-score, and then using that z-score, you're going to find the proportion or the probability. All right. So let's see. Discard. Okay. All right, so let's get back to that one. Okay. All right. So again, like that triangle stated, right? We're going to go from the sample mean to the z-score to probability. All right. So let's get all of our information, right? In order to take the mean and get to a z-score, right? We need to put it into the z-score formula. But before we do that, all right, we need to calculate the standard error of the mean, right? So standard error of the mean is going to be the standard deviation divided by the sample size, right? And so for this, the standard deviation is 4, and the sample size is 4. So we're taking the square root of that. And that gives us 4 over 2, which gives us a standard error of the mean of 2. All right. And so then we're going to plug it in to this z-score formula for sample means, right? And so this is going to equal, the sample mean is 22 minus the population mean of 20 divided by 2. That's going to give us 2 over 2, which equals 1. All right, 2 over 2, which equals 1. But we're not done yet. They didn't ask us for the z-score. What they asked us was to find the probability, right? And specifically, the probability is, what is the probability of obtaining a mean that's greater than 22? So let's draw the distribution out and see what we're looking at. So here's the population mean, right? Population mean is 20, right? The sample mean is 22, so it's greater than the population mean, so it's somewhere over here, right? And it's saying, hey, what is the probability of obtaining a mean greater than 22? So we're looking for this part right here. So we're looking for a tail. And if we wrote it out as a probability, it's P, and in parentheses, the event. The event is finding a sample mean that is greater than 22. All right. And so, so now we are going to take the z-score of 1, right? To take the z-score of 1, we're going to go into our unit normal table and look for the z-score of 1, and then cross over into column C and look at what the tail, what the proportion is in the tail for a z-score of 1. All right, so let's do that. All right, I'm going to make sure you can see this. Okay, so if we have a z-score of 1, right, which is right here, and we're looking in column C to find what is the proportion in the tail, it is going to be 0.1587. All right, 0.1587. All right, or 15.87%. All right, so now let's go to question 3. So in this one, a random sample with a sample size of 4 is obtained from a normal distribution with a population mean of 40 and a standard deviation of 6. What is the probability of obtaining a mean greater than 46 for this sample? So let's see. Well, we won't do that question because we kind of did that question already. All right. So you kind of know the gist of it. So we'll skip that. All right. All right. And so here are the answers to the questions. All right. And here are the directions on how to do them. All right. Okay. So here's another learning check. All right. So in this one, doing the first question, a sample is selected from a population with a mean of 90 and a standard deviation of 15. Find the z-score for the sample mean for each of the following samples. All right. So if we were drawing our triangle, right? Well, so in this one, they're giving us, right? They're giving us the raw scores, right? Let's see, I think it was also. So just saying find the z-score. So this one, we're just going to take the information they gave us. We're going to find the standard error, and then we're going to plug it in to find the z-score, right? So in this one, let's see. So the equation to calculate a standard error of the mean equals 15 over the sample size, which in this one, the sample size here is 9, right? So square root of 9. So that's going to give us 15 over 3, which gives us 5. All right. And so with this, now it's asking us find the z-score, right? So we already found the standard error. Now we can plug that standard error that we found into the z-score formula, right? So z equals the sample mean minus the population mean over the standard error of the mean. And so the sample mean is 100, right? So it's 100 minus the population mean of 90 divided by the standard error of the mean, which we calculated as 5. So that gives us 10 over 5, which gives us a z-score of 2, a positive 2. All right, that's how you answer number 1. I won't go to do number B, to do question B, because that's the same kind of question. All right, so in this one, number 2 is asking us, what is the probability of obtaining a sample mean greater, right, greater than 60 for a random sample with 16 scores selected from a normal population with a mean of 65 and a standard deviation of 20. So it's asking us to find a probability, right? And they started by giving us the the sample means, right? So we're going from the sample mean, right, to z-scores, then to probability. All right. Let's see. So I won't do that question again because I kind of already done that one. All right. So that's how you do it. So you would take the mean, then you would get the standard error of the mean, and then plug it into the z-score formula. And then you would draw your distribution and find out if you're looking for a body or a tail, given the probability question. And then look up the z-score in your unit normal table. And then look under either row B or row C, depending on if you're looking for a body or a tail. That would give you your answer. So I am gonna do number 3, right? So what are the boundaries for the middle 50% of all possible random samples with a sample size of 25 scores selected from a normal population with a population mean of 80 and a standard population standard deviation of 10, right? So in this one, right, let's see here's our distribution, right? And it's asking us for the middle 50%, right? So all this stuff right here. So what we know already is that if we're going from percentages to, right, so I'm trying to find us where we're not going from percentages, but they're giving us the sample means and asking us to find boundaries, right? Well, in this one, we are going to, give me 1 second. 1 second. All right. So we know that for the middle 50% is going to be broken up into 25%, right? On the left side and on the right side, all right, which is actually 0.2500 and 0.2500. All right. And so what we can do with this is that we are going to also calculate the standard error of the mean, right? So the standard error of the mean, uh, well, before we calculate the standard error of the mean, we have to calculate the z-score, right? We have to, we wouldn't be able to find this without a z-score. And so, I'm sorry, give me 1 second, this technical difficulties. All right. Okay, sorry about that. I had someone calling me. All right, so let's continue. So for this one, we are going to go into our unit normal table and look up the corresponding z-score for 0.2500 in column D. Find out what that is. So we're looking for the number that is closest to 0.25 in column D. 0.25 in column D. And the number closest to that, right, is going to be, these are two numbers that are really close. It's 0.2486 and 0.2517, but 0.2486 is 1 decimal place closer. So that corresponds to 0.67, right? 0.67. So let's go back to our thing. So our z-score equals 0.67, all right? All right, so then we are going to plug the z-score into our sample mean equation, right? And our sample mean equation is the mean equals, right, equals the population mean plus the z-score times the standard error of the mean. All right, well, we don't have our standard error of the mean yet. So let's calculate that. So to calculate standard error of the mean, we have the standard deviation divided by the sample size, divided by the square root of the sample size, which equals 10 over square root of 25, right? Which is 10 over 5, which equals 2. So our standard error of the mean is 2. So now let's plug everything into our sample mean equation. So our population mean, right? And in fact, we're trying to find the boundary. So there's two scores that we're going to get, right? And so that is going to be, the first one is going to be the population mean of 80, right? Plus the z-score of 2 times the standard deviation of 10. The other one is going to be um, -80 minus 2 times the standard deviation of 10. Oh, wait a minute. No, so that's wrong. That's why it's okay. I'm doing this all wrong. Okay, sorry about that. All right, so it's going to be the z-score of 0.67, right, times the standard error of the mean, which we calculated, which was 2, right? And this one's going to be minus the z-score times the standard error of the mean, which is 2. And that's going to give us the top boundary is going to be 81.34, and the lower boundary is going to calculate to 78.66. All right. And so that's how you would do number 3. Again, these are essentially the same questions as chapter 6, except instead of using raw scores, we are using sample means. All right. So here are the directions to answer those questions, and here are the answers to the questions. All right. All right. So a little bit more about the standard error, right? So there will usually, again, be a discrepancy between a sample mean and the true population mean. So this discrepancy is called a sampling error. So the amount of sampling error is going to vary across samples. The variability of sampling error is going to be measured by the standard error of the mean. All right, so here's an example of a typical distribution of sample means. So all these square boxes are sample means, right? So each of the small boxes represent the mean obtained for one sample. So 50% are of those sample means are smaller, 50% are smaller than the sample mean, 50% are bigger than the sample means, with most of the means being really close to the center of the distribution. Some are going to be close to the tails, and these are extreme samples that do not accurately represent the population. All right, so this one goes right here, right? Here's a population mean. All these boxes are sample means. 50% are below the mean, the population mean, and 50% are above the population mean. Most of the sample means are going to be relatively close to the population mean. However, there are going to be sample means that are in the tails that are very, very far away from the population mean. We are going to consider those in the tails to be extreme samples. Before it was extreme scores. Now we would consider those to be extreme samples. All right. So here is the distribution of sample means when the sample sizes are 1, 4, and 100. And we kind of got the gist of this already, right? But the distribution of the mean distribution of the sample means when the sample size is 1, your standard error equals your standard deviation, which in this case was 20. So this is what the distribution would look like. However, if we had a distribution of sample means where we increase the sample size to 4, right? Well, our standard error of the mean is 10, right? Whereas it was 20 over here. Our population mean is going to be the same, because again, if we average all of the sample means, it's going to be equivalent to the population mean, right? But now if we had another distribution of sample means and we increase the sample size to 100, well, that's going to make our standard error smaller, right? Because standard error is going to is going to decrease as the sample size increases, right? But the population mean is still going to be 80, right? All right. And so that represents, again, the law of large numbers, which we talked about a couple of slides ago. So how does the standard error look in the literature, right? We talked about a couple of weeks ago what the mean and the standard deviation look like in the literature. What does the standard error look like in the literature? Well, the journals are going to vary in how they refer to a standard error, but they are frequently going to use this SE or SEM. And these are often reported in a table along with the sample size and the sample means for different groups in an experiment. And they could also be added to a graph. So in the next figure I'm going to show you, the mean is going to be represented by the height of the bar. And the brackets that come out of the bar represent one standard error above the mean and one standard error below the mean. All right, so here is where the mean is at. This is the height of the bar. So these are where the means are at. The brackets coming out of it represent one standard error above the mean and one standard error below the mean. All right. So when you see these in a chart, this is what is going on, right? If the what are called error bars, these right here, right? If the error bars overlap, so if these bars overlap with each other, right? For let's say we had group A and group B. If these bars overlap with each other, and the overlapping region also includes the means of the sample, then there is strong evidence that there is no difference between the means. However, right? However, if the error bars overlap and the overlapping region does not include the means of the samples, then there is strong evidence of the population being similar or different. All right. 3, if the error bars do not overlap at all, so in this case, the bars don't overlap at all, in our case, in this particular slide, well, then there is strong evidence that the two groups are in fact different. All right, so you're going to see these kind of bar charts, right, with these, error bars a lot in research papers. So that's how to interpret them. All right. So this is kind of the same, right? So and this one is a line graph where each dot represents a sample mean, right? In different trials with 2 different groups. There's group A, they did 4 different trials and they calculated the sample means for each of those trials. And they did a group B, right? And they calculated the sample mean for those trials as well. The bars coming out, those brackets coming out, are error bars, and it represents 1 standard deviation above the mean. I mean, 1 standard error above the mean and 1 standard error below the mean. All right. So that's how you interpret those as well. Okay. So looking ahead to inferential statistics, right? So like we've been saying for the last couple of weeks, inferential statistics use sample data to draw general conclusions about populations. Sample information is not going to be perfectly accurate, right? Because of sampling error. And the differences between a sample and a population, they're going to introduce levels of uncertainty into the inferential process. All right. And so statistical techniques use probabilities to draw inferences from sample data. So let's go back to our population of rats, right? That we started with all the way in week 1, in chapter 1. So let's say we have a normal population of adult rats, right? And the population mean for them is 400 as far as their weight, and the standard deviation is 20. Then we get a sample of 25 rats. We're going to treat those rats with some kind of formula or program or something of the sort. All right. And then those rats then become a treated sample of 25 rats. And so the purpose of the study is going to be to determine whether the treatment, in this case, is a growth hormone, has an effect on the weight of the rats. So the distribution of sample means, right, using that previous slide, the distribution of sample means for samples of 25 untreated rats. Let's say we wanted to find out where the boundaries are of 95% of the sample means, right? Well, we kind of did this question a little bit last week, all right? But now instead of using scores, we're using sample means. So in this one, right, in order to find out, well, let's go back. in order to find out where 95% of the sample means lie, well, that's a middle question, right? So let's draw our distribution, right? Here is our mean. And here is where here's the boundaries where 95% of our sample means lie, right? So we know that in order to find out where those boundaries lie, right? We are going to be using column D in the unit normal table, right? So 95% divided by 2 gives us 47.5%, right? Which is equivalent to 0.4750, right? As far as a proportion. So now we're going to go into the unit normal table, into column D, right? To find out the number that is closest to 0.4750, all right? 0.4750. And we have that exact number here, 0.4750. And that is a z-score of 1.96, right? So z-score of 1.96. So this is where the boundaries are. So on this side, below the mean, this is a z-score of negative 1.96. And this is a z-score of positive 1.96. All right. And so in the population, right, the population mean was 400. And the standard deviation was 20. And we had a sample size of 25, right? So if you want to know what those exact numbers were, right, we would plug it into the X equation, right? So for the the sample mean equation. So that is going to be the sample mean equals the population mean plus the z-score times the standard error of the mean, right? And so for this one, the population mean is 400 plus the z-score of 1.96 times the standard error of the mean. Now, we haven't calculated the standard error of the mean yet. So let's do that. So the standard error of the mean is the standard deviation divided by the square root of the sample size. So that is going to be 20 divided by the square root of 25, which equals 20 over 5, which equals 4. So the standard deviation equals 4. But we have two boundaries, one positive, one above the mean, which is a positive 1. Well, one above the mean and one below the mean. So the other one is 400 minus 1.96, right, which was a z-score times the standard error of 4. And so if you calculate those, this equals 407.84. Oh, yikes. Give me a 407.84. And the one that's below the mean calculates to a score of 392.16. All right. So what we're saying is, hey, if we treated the sample of rats, all right, with the growth hormone, right, and the rat's weight in that treated sample, the sample mean, right, the sample means, if the sample means are beyond 407.8 or smaller than 392.16, we are going to say that those are extreme scores, right? Those are extreme scores, and that we're going to say the treatment works. The treatment has some kind of effect, all right? Because those sample means are so unlikely to have occurred simply by chance, all right? And so that's a foundation of what we are going to talk about in the next chapter when it comes to what is called hypothesis testing. All right. So let's continue. All right. All right, so all of these questions are essentially versions of the question that we just did on this lesson check. So I won't go over those again. All right. All right, skip that, skip that, skip that. Okay. All right, so we have come to the end of chapter 7. I want to thank you for sticking around. Hope you learned a lot. Again, if you have any questions or any of this, you can email me on at my email or inbox me in Canvas, or attend my office hours, which are printed on the syllabus. Or if you can't meet during my office hours, you can always do some kind of work it out on some kind of Zoom call meeting. I thank you, and you have a great day, y'all.